Video 3, we are going to continue on with our transforming and combining of random variables, discrete and or continuous, it doesn't matter. But we are going to get into some more advanced problems than what we did in video 2. Now, we talked about in video 2 two different types of rules. We talked about linear transformation rules. So we talked about if there was some sort of an addition or a subtraction type of transformation going on versus a multiplication or division type of transformation, that in terms of the mean, if we wanted to transfer one mean into a different mean through a linear transformation, that multiplication did affect the mean, and we would also have to apply the addition transformation as well. So addition and multiplication both affected the means. But in terms of standard deviations, that only a multiplicative change would affect our standard deviation. So if there was some sort of addition or subtraction change, we just learned that we needed to ignore that particular transformation for just only our standard deviations. Now, the second thing we talked about was actually combining random variables. Now, the one thing that we solely focused on in video 2 was combining two random variables. But these rules will apply if we wanted to combine more than two random variables as well. And we'll look at some examples of that today. But in general, if we wanted to add random variables for our means, we got to do exactly what we thought. We got to add the individual means to get the mean of this new combined random variable. And for standard deviations, they never did what we thought they should do. We had to square our standard deviations, add them together, and then square root. And then we talked about at the end of video 2, sometimes we may need to subtract our random variables. And so if we want to have a new combined random variable that is the difference of two, then we would get to subtract our means. And with standard deviations, though, even though we're subtracting our random variables, we would still have to add our squared standard deviations and then square root. And our standard deviation formulas were all dependent on if x and y were independent random variables. And you have to be told that information. Now, both of these rules, none of these rules are on the AP Stats formula sheet. So I will not give them to you for my chapter test. So don't expect to see these. You're going to have them memorized. Now, in the last video, we talked about Allison and her sister Julie, and they're swimming, and I gave you the times of each, and I had you explore what the mean difference and what the standard deviation difference was in their times. So let's kind of revisit this problem here. So Allison's times were normally distributed with a mean of 37, standard deviation of 1. Her sister Julie, who's faster, but is less consistent than Allison, her times are normally distributed with a mean of 33 minutes and a standard deviation of 2. And on any day, their times were independent. So right now, here's what we can talk about. If we talked about Allison, we'll call her A. Allison follows a normal distribution with a mean of 37 and a standard deviation of 1. And Julie, we'll call J, also follows an approximately normal distribution with mean of 33 and a standard deviation of 2. Now, the question that I posed at the end of video 2 was, could Allison ever beat Julie? And that's what we're going to try to figure out. Now, if you think about it, we said Julie's faster, right? Her mean times 33, Allison slowpoke, 37 minutes. Oh my gosh, so slow. But remember we said Julie is less consistent than Allison. She has a higher standard deviation. So might there ever be some times where she's just really inconsistent and Allison's on her A game? Could Allison ever beat Julie? So here's what we're going to figure out the probability of. We're going to figure out what is the probability that Allison beats Julie. But we got to think about what would that look like in terms of A and J. So if Allison were to ever beat Julie, in terms of swimming, that would have to be a faster time, and a faster time would be a smaller number, right? So symbolically, that would mean that Allison's time would have to be smaller than Julie's time. So this is what we want to figure out the probability of. But we can't leave our inequality like this because we cannot compare these two distributions the way that they are. what we're going to have to do is combine our random variables. And so what we're going to do is subtract over. We're going to treat this inequality like it's an equation. And I'm going to put the j, Julie's time, over with Allison's side. So really we're looking at the difference of Allison and Julie's time, that it would need to be less than j minus j would leave me with 0. And so now I get to use this number here. That is going to be a part of my normal calculations. Now, if I subtract two normal distributions, Allison was a normal, Julie was a normal distribution. If I subtract a normal distribution and a normal distribution, the combined random variable of the difference of their times is still going to be a normal distribution. So that's the main thing to remember here, is a normal minus a normal, still a normal distribution. A normal distribution plus a normal distribution is still a normal distribution. It just happens to be a bigger normal distribution. So this is what we want to figure out. What is the probability that the difference of their times is less than 0? Right? That would mean that Allison's time is smaller, Julie's time is bigger. A smaller number minus a bigger number would produce a negative number, and negative numbers are less than 0. So, the distribution of times of this new combined random variable, a minus j, this is what we talked about at the end of video 2, was what their mean and their standard deviations would be. So all I did to figure out the mean of a minus j was I took their mean times and I subtracted them. So Allison's was 37, Julie's was 33, so I got to subtract those. So the mean difference of their times was 4 minutes. And then I used the standard deviation formulas. The two standard deviations were 2 and 1. So I had to square both of their standard deviations. What was Allison's? Allison's was 1, Julie's was 2. And so this ended up being the square root of 5, which came out to be approximately 2.236. So I have a shape for this distribution. I have a mean for this distribution. I have a standard deviation for this distribution. So imagine here is a normal distribution representing this random variable a minus j. And so I know the mean in the middle is, on average, there's a 4-minute difference between their times. Now, what I want to mark in this particular graph is, where would I find 0? So 0 would have to be to the left of the mean, right? And it's going to be what? Not even 2 standard deviations below the mean. So I'm just going to approximate, I don't know, maybe right here. We'll call that 0. So where are all the instances that are less than 0? Well, that would be all of these instances. And now we get to go back and use some old school Chapter 2 normal CDF material. So we said this a minus j distribution is approximately normal. And so the lower bound of this shaded region would be negative infinity. The upper bound is right at 0. The mean is 4. And the standard deviation is 2.236. So let's figure out, what does this come out to be now? So let me go to my calculator. So we go to normal CDF, second variables, option 2. Lower, negative infinity, that will work the way it is. Upper bound, 0. Mean, 4. Standard deviation, 2.236. So about 3.681. 3.681% of the time, Allison can beat Julie. So it's not going to happen that often, right? Not going to happen very often that Allison will beat Julie, but is it impossible? No, there is a slim chance Allison can beat Julie. Second example. A resort rents boats to customers. Each boat can safely hold no more than 800 pounds. The distribution of weights of adult males is approximately normal, with a mean of 190 pounds and standard deviation of 10 pounds. If the weights of individual passengers are independent, what is the probability that 4 adult males will exceed the acceptable weight limit of 800 pounds? So first, let's talk about the information that they told us. They told us about the distribution of adult males' weights. And they are approximately normal with a mean of 190 and a standard deviation of 10. So I'm going to call, I don't know, X. Let's let X, we got to define our random variable. X equals the weight of one adult male. And X follows an approximately normal distribution with mean of 190 and a standard deviation of 10. So that's great. That's great if I have one adult on this boat. But I don't have one adult male on this boat. I have 4 adult males on this boat. So I need this new random variable. And so here's where it's going to get different. We're not just going to be talking about 2 combined random variables. I need a whole boat full of people. Well, that would represent 4 adult males. And so I'm not just going to have one X. And here's where we got to talk some differences between algebra and statistics. So I have this new combined variable where I'm going to take one adult male, an X, and I'm going to add to that another adult male, an X, and add another adult male, an X, and another adult male, an X. Now you might be going, well, hey, algebraically that's 4X. And I would agree, that is 4X. But in algebra, X represents a singular value. So if we were to add a singular value to itself 4 times, yes, that is equivalent to 4X. But X statistically in this problem represents the weight of one randomly selected adult male. So here's a situation I want you to consider. Let's say this first X, this is me. And let's say this other X is, I don't know, your dad. Do me and your dad weigh the same amount? We could, we might, but are we going to weigh exactly the same? Probably not. So my weight X and your dad's weight X and your uncle's weight X and your cousin's weight X, we don't necessarily all weigh the same amount. So we can't just call that 4X. So this is going to be kind of weird that we're going to leave this, and we have to leave this as X plus X plus X plus X. Now, what you might do is say, let's call that a new random variable B for the boat. Okay, so then you could say, all right, what is the mean of the boat? What is the standard deviation of the weight on the boat? But I'm going to leave this as this new random variable X plus X plus X plus X. Now, this new random variable, if this is a normal distribution plus a normal distribution plus a normal distribution plus a normal distribution, say that 5 times fast, it is also going to be a normal distribution. But now we got to talk about what is the mean and the standard deviation of our 4 adult males. So what is the mean of X plus X plus X plus X? Well, our rules say that we're going to get to add together the individual means. Well, what is the individual mean for each adult male? Well, it is a constant value. It's 190. So now here, algebraically, we could call this 4 times 190, which is 760 pounds. So the mean of our 4 adult males is 760. What's the standard deviation? All right, so let's move all this stuff up here. So now sigma of X plus X plus X plus X. So we said square root. Now normally we just had one standard deviation squared plus another standard deviation squared, but we've got 4 of these. So it's going to be sigma squared of X plus another sigma squared of X plus another sigma squared of X plus another sigma squared of X. But what do each of these sigma squared plus or sigma squared X's represent? That's just the standard deviation of one adult male. So 10 squared plus 10 squared plus 10 squared plus 10 squared. So this is really 4 10 squareds, right? And 4 10 squareds would be 4 100s, which is 400. And the square root of 400, thankfully, gives us a nice whole number of 20. So the standard deviation of our 4 adult males is 20 pounds. So there's kind of our initial work here. Now, proceeding on. What is the probability that the 4 adult males will exceed the acceptable weight limit of 800 pounds? Here is our random variable, X plus X plus X plus X. And like we said, that follows a normal distribution with a mean of 760 and a standard deviation of 20. So I have my random variable, I have my inequality, and I've got a number to compare it to. So remember, the mean of our 4 adult males is 760 pounds. Where would I find 800 pounds at? Well, above the mean. How far above the mean? Well, really exactly 2 standard deviations above the mean. So I'm going to say right there, there's where 800 is. Which way do I want a shade of the 800? I want to go greater than 800. So we can tell just based on our picture here, it's not going to be that high of a probability. So now if I jump in to my normal CDF, we are starting at 800 as our lower bound. We're shooting up to infinity with a mean of 760 and a standard deviation of 20. What does that come out to be? And before I go on to my calculator, you might go, hey, if this is exactly 2 standard deviations above the mean, couldn't we use the empirical rule, the 68, 95, 99.7 rule? And you could. So there's really 2 different possible answers you could give me here. The empirical rule answer or the calculator answer. And either one would be accepted on the AP exam. So normal CDF, starting at 800 pounds, going off to a boat full of sumo wrestlers. Mean, what do we say, 760. Standard deviation, 20. We should get something close to 2.5%, because that's what the empirical rule answer would be. So 2.275%. 2.275%. And there's our probability that our 4 male adult passengers would exceed the weight limit of 800 pounds. Not going to happen that often. But again, it could happen, just not likely. Now our final example. So I'm going to set this one up with you, and then you are going to finish the rest of this problem as part of the you do problem. So Acme makes weightlifting bars. The weight of each bar, notice that B bar, is independent and normally distributed with a mean of 720 ounces and a standard deviation of 4 ounces. The bars are shipped 10 to a box to retailers. The weight of an empty box, notice the big X, is normally distributed with a mean of 320 ounces and a standard deviation of 8 ounces. What is the probability? The weight of a full box. What's in a full box? 10 bars are in a box. Weighs less than 7,500 ounces. So here's the question they're asking. What is the probability that a full box, we're going to have to come up with a random variable name for a full box, but for right now, we'll just call this full box, weighs less than 7,500 ounces. So what does that come out to be? Now, again, we need to talk about what does a full box represent. So a full box, we said the bars are shipped 10 to a box. So we're going to put 10 bars in a box. So we don't just have one B for a bar, we have 10 Bs for a bar. But can I call 10 bars put together 10B? Can I do that algebraically? And no, because not every bar is the same exact weight. There is a standard deviation to them. So the bars will vary a little bit in weight. So I can't say that bar plus bar plus bar plus bar 10 times is 10B. That's not true. So let's get our 10 bars. Bar plus. Now, I'm going to do this. I'm not going to write out 10 Bs. I'm going to pretend like, hey, look, I wrote out 10 bars. This represents 10 bars. And with those 10 bars, they get put in a box, which I said, let's call the box X. So now 10 bars plus an X for a box, this represents a full box. Now, if we wanted to, we could call all of this a singular new random variable, like maybe F for a full box, but we don't have to call it just a singular random variable. We could just leave it as this, that B plus blah, 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 plus B, 10 Bs, plus an X, there represents a full box. Now, let's talk about what they told us about bars and boxes. They said the mean of one bar is 720, and the standard deviation is 4. And they told us that these values were approximately normal. And the mean of a box was 320 ounces. and the standard deviation of a box was 8 ounces. And they also said that these weights followed a normal distribution. So if we're going to have a normal distribution plus a normal distribution plus a normal distribution plus another normal distribution, in the end, this distribution will be approximately normal as well. And we need that to happen so that we can use normal CDF in order to calculate said probability. So we know that this new combined random variable is approximately normal, but now let's figure out what's the mean and the standard deviation of this full box. All right, so the mean. Here's what we'll do. Let's move that up here. We'll shove this up there. Perfect. So now the mean of b plus dot 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 plus b plus an x just means that we can add all of these individual means. So we have mu sub b plus another mu sub b plus dot 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 plus a 10th mu sub b plus a mu sub x. Now altogether, remember, these represent all the same value. This is 720 and 720 and 720. So we really do have 10 720s. And then we get to add in one mean of a box, 320. So here's 7,200 plus 320. Overall, the mean weight of the entire box is, no, if I can do my math right, 7,520 ounces. So I'm going to put that over here. The random variable b plus b all the way up to 10 b's plus an x was approximately normal with a mean of 7,520, and we still need a standard deviation. Now I'm going to erase my mean work and get to my standard deviation. So the standard deviation of our new random variable b plus dot 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 plus b 10 times plus x will be equal to giant square root. And now these are all random variables, so even though you might be going, hey, we're adding. Didn't you say adding doesn't affect standard deviations? Yeah, if we were adding numbers, but these are random variables, so it doesn't apply same way. So we'll have sigma squared of the first bar plus sigma squared of the second bar plus the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, and the 10th bar plus the one box. Now, square root. We do have 10 of these sigma squared of b's, right? So I'm just going to simplify this for right now to be that. And then we just had the 1x. Now we're going to plug in what sigma was, sigma sub b, which was 4. So this is 4 squared. And then our one box standard deviation was 8 squared. So now let's see, what's that going to come out to be? Let me get some space in here. Boo, 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 boo. So this is 10 times 1, or 10 times 16, plus 64. That's 160 plus 64, which again, it's the square root of the whole thing. Square root of 224, square root of 225 is 15. So this is like 14.9 something. All right. So I'm going to show you on the next screen what that really comes out to be. But there's the standard deviation of the entire box of 10 bars. So now, 14.97, there we go. So now what I want you guys to do is really answer the probability question that I posed. What is the probability that a full box, again, 10 B's plus an X, is less than 7,500 ounces? And again, we've got a approximately normal distribution. We've got a mean of the whole box. We got a standard deviation of the whole box. Now tell me what that comes out to be. And we'll talk about that the next day.